some sort of comfortable screen. We'd like to remind everyone also to complete the evaluations. I'm just going to repeat what I said earlier. Evaluations are to be collected by you and then giving to us all, not at the end of the day, at the end of the workshop. All probably 18 evaluations or 19 evaluations are to be given to us during the end of the workshop. And you've seen the way the evaluation, they're all standardized evaluations. You have to choose which tutored a small group tutorial. May I ask Alfonso to come up to the podium? All right, so we're starting with the next session, which I much look forward to. So Dr. Alfonso Iorio is going to talk to us about measures of treatment effect.
Welcome back. I hope you enjoyed the tutorials, and if not, I will try to convince you that tutorials are much better than listening to things like this. So, measures of treatment effects. So we should by now know what we are talking about. We will just give a more thorough consideration of some of the aspects we have been discussing during the day. In particular, I'd like to point to you some properties of relative and absolute measures of effect, relative risk reduction, absolute risk reduction of risk difference, number needed to treat, and what makes the need for odd ratio and hazard ratio. And that's the first part of the talk. The second one will be about pooling effect size. So initially, let's see how we measure the effect, and then how we can combine effect across studies, fixed and random pooling, network myth analysis. Just concept, but just to give you the basic pieces to be able to interpret on your own why sometimes we use one approach, sometimes another, and what we gain out of each of them. And finally, aspect of study design, then impact on calculation and interpretation, adjusting the analysis, stratification, how to judge about attrition bias. Again, you should now know a bit more after the tutorials. We'll try to go back together and fix some concept. So let's start with something interactive. I know that you strive for being called to action. The setting now is a willingness to fund a mammography screening. We are providing support to the Ministry of Health or whoever is that is looking into, do we want to push for mammography screening? Do we have funds to spend? And in particular, which approach do we take? Now, I'm presenting you three different programs. Program A has scientific evidence showing that it can reduce the rate of deaths from breast cancer by 34%. Okay? That's one option. Second option is Program B. Program B increases the rate of patients not dying from breast cancer from 99.82% to 99.88%. So after adoption of Program B, the survival will be 99.88. And finally, Program C is a program that has evidence showing that if you screen every year for 7 years, 1,600 women, you prevent 1 death from breast cancer. Now, I've done my job. I've presented you the evidence. You are the Ministry of Health, and you tell me which one you prefer. So who is in favor of adopting program C? No one? I would. She would. Two of us would adopt program C. Who would like to adopt program B? No one? You would, and I would. I'm a counselor, so it doesn't really matter to me. I'm for all the programs. But we too vote for program B. Then who of you vote for program A? Many of you. Who didn't vote? I want to see. Okay, you didn't vote, you didn't vote, you didn't vote. Why you didn't vote? Because you are lazy? No. Because you are uncertain. So which one you are uncertain with? A and B, B and C? So you see that every presentation had to convince someone. There were two of us, one of you voting for C, one voting for B, a handful voting for A, many others said, we don't see it clear, we don't vote. Okay, now you have done this already. Let's look at this figure. The death rate in the control group is 0.2, and the death rate in the treated is 0.16. If you express the change from 0.16 to 0.2 as a relative risk reduction, is a 20%. You take 16 over 20, and then you divide it by the baseline risk, and you get 20% relative risk reduction. You reduce the risk in the control by 20% of what it is. If you consider this other situation where the risk in the control group is 0.057 and you reduce it to 0.045, is a relative risk reduction of 21%. So it's very close to the one above. The risk is different, is 0.20 in the upper example, 0.5. So 20% in the first example, 5% in the second example, but still the relative risk reduction is 20%. The absolute risk reduction, though, is different, because in the first case is 4, 20 to 16 is 0.04, by 100 is 4%. In this case is 1.2. 57 to 45 is 12. 0.012 multiplied by 100 is 1.2. If you calculate the number needed to treat, is 25 up here and is 83 down here. But the relative risk reduction is the same. This was the introduction to the breast cancer case. So if you consider 0.18 the death rate in the non-screened and 0.12 the death rate in the screened, 18 in 10,000, 12 in 10,000, the relative risk reduction is 34%. So case A, that you all, well, not you all, but many of you supported as the most effective, was a 34 relative risk reduction going from 18 in 10,000 to 12 in 10,000. Okay? The death rate goes from 0.18 to 0.12, which is survival goes from 19.82 to 19.88. This was case B. Is exactly the same as case A. Is the same intervention. And the absolute risk reduction is 0.06, which was case C. The number needed to treat for an absolute risk reduction of 0.06 is 1,667. Case C was 1 in 1600. So there was no real reason to choose between the three interventions. The three interventions were exactly the same, just their efficacy was expressed in relative risk reduction, change in the survival rate, or number needed to treat, but it's the same. But you see how only one wanted this one wanted this here, and many wanted this one here, just because numbers are misleading. But the underlying intervention is the same. That's why it's important to understand numbers. I know that you decided very likely to do medicine because you didn't like math, but unfortunately, math comes back here like anywhere else. Now, consider a patient with DVT. He has completed 6 months of anticoagulants, and now we come to you and the question is, do we continue or not? And now the doctor tells the patient that if he continues, his risk of having another clot will be reduced by 50%. If you are the patient, what do you think? Do you understand what, okay, you continue taking the anticoagulant and your risk is decreased by 50%. Are you happy? Yeah. Well, for sure, if the risk was going up, you would be less happy. But is a reduction of 50% enough for you to be truly happy? You have to take warfarin, you have to go for monthly INR, you have risk of bleeding, you cannot jump anymore from planes with a parachute or do bumpy jumping or whatever you like to do that put you in danger of bleeding. So, is there something missing? Anyone want to attempt to tell me what's missing? The number needed to treat, the absolute risk. If the patient belonged to this population, the risk of a second event is 30%, would go down to 20, 10 events saved. If the patient is here, 10% would go down to 6, 4 events saved. Or this is a 67% reduction, not 50. But if the patient has a risk of 1, we'll go down to a bit less than 1. So what different is the baseline risk, which let you calculate the number needed to treat or the absolute risk reduction. If we assume that the treatment is not 50%, but the risk reduction is 0.67, the risk difference will be 10, 3, 1. So we need absolute numbers to make decision. Look at this example. VTE prophylaxis in a 65-year-old with a COPD exacerbation, getting to the hospital, but you would expect that in 3 days he will be walking again. You do prednisone, you do antibiotics, and you expect the exacerbation to get controlled quickly. The relative risk reduction of giving him prophy is 50%, but the baseline risk is 4 in 1,000. That's the rate of VTE in this population. 4 in 1,000 patients like that got a VTE. So indeed, you treat 500 patients to save 1 clot. But the relative risk reduction is 50%. Consider starting an ACE inhibitor in a class 2 and NYHA heart failure, where the mortality rate at 1 year can be cut down by 25%. Now, the mortality rate in that class of risk is 20%. So 20 of those patients, 20 of 100 patients like those, or 1 in 5, will die at 1 year. So even if you cut down by 25% the risk difference is 5. And every 20 patients you treat, you save 1 life. So if you have only 1 bullet, you would prefer this treatment here, even if the risk reduction is less than that one. Because here, the risk reduction is high, but the baseline risk is low, and you get to treat many to get something. Here, this is high, you cut it down by a lower proportion, but you get a better benefit larger benefit for the population. Okay, if this was not confusing enough, from now on, I have much more confusing stuff. So if you still feel you understand, don't be hopeless. You will stop understanding at some point. I'm joking. I'm trying to make it simple, but is not so simple. So I'm trying to get rid of odd ratio. Now, odd ratios are, the risk is how many events out of the population. The odd ratio compares the events and the non-events. So the odds, I don't know if you gamble here in Kuwait, if you like gambling. I don't, I'm Italian, but in Canada and all the Anglo-Saxon world, they gamble on everything. To gamble, what counts is not how many times 27 come out of the roulette, but is how many times is 27 and not another number. Is the odds of having two different positions. So is the odds of black as compared to the odds of red. Is not how many times black out of all, because you don't stay there lifelong. So you are not really worried about how many times these come out of the entire draw. It's the relative number of draw. So the odds is the chance of winning compared to the chance of losing, not the chance of winning out of the doing the run. Now, when the numbers are small, 0.1 or 1 over 0.9, which is the odds, are similar. 0.2 is still similar. It's 0.2 over 0.8 is 0.25. It's not identical, but it's similar. But now, as soon as you go up with the risk, you see that it diverges. So 0.3 is already 0.5 on this side. 0.6 is already 1.5. 0.8, 80% risk, becomes a odds of 4. Now, if someone of you is clever and self-protective, should ask, why the heck you need odds? Why don't we stay with risk that we understand? 80% of patients get whatever disease you want. Why we have to say, let's say, patient with diabetes have 80% increase in the risk of having an infarction, a myocardial infarction. I understand that. Patient with diabetes as compared to patient without diabetes, they have 80% more risk of cardiovascular event. Why you have to tell me that the odds of patient with diabetes as compared to the odds of patient without diabetes is 4 times higher? I'm not betting on survival of patient with diabetes. I'm trying to cure them. Well, the reason is, the only reason to use odd ratio is that they are much nicer to pool in meta-analysis, first. Second, they can be calculated out of case control study, where you don't have the denominator, where you don't have the population, but you only have cases and controls. You can only calculate odds, because you don't know what the population is. You don't know the true incidence. You only know the different probability of 2 different groups. So you are in the kingdom of odds. But odds are not what we need to think, and you can't calculate number needed to treat out of an odd. So the take-home message for you is that for low risk, odds and relative risk, you don't matter what the difference is, you consider them the same, up to 30% risk. Above 30% risk, take a paracetamol, prevent headache, and do the maths. Now, I'll show you what happens if you have a treatment that reduces mortality. Control group, 40% mortality, 60 are alive. Treatment group, 50% reduction, 20 dead, 80 alive. If you calculate the risk is 20 divided by 40.5. If you calculate the odd, is 25, 67.37, because you don't consider anymore 20 out of 100, 40 out of 100, but is the sum gives 100. So you see that this is the ratio, this is the odds. And it goes the other way as compared in a previous table. So it's really complicated. Up to a risk ratio of about 0.3, you can consider them identical. Time to event. Time to death. Is that relevant? Well, in the end, everyone will die. So the relative risk reduction, if you set time at infinite, is always 0. Those with diabetes will die, and those without diabetes, they will die as well. It's a matter of, if you wait long enough, everyone will die. Okay? That makes statistics and epidemiology useless. If you look at, is there any treatment that gives you eternal life? No. Okay. But if you are interested in how long you survive, there would be a reasoning to do about competing cause of death. I can save someone from dying from PE, and then he will die of cancer. I can save him from dying with cancer, he will have an infarction. He will die one way or another. But you have to take the thing in small pieces. So let's consider one cause of death, let's consider one intervention. We might be able to avoid the event or to delay the event. Both are reasonable outcome. If I'm interested in delaying the event, I need to consider not only how many events I have, but when I have the event. So if I'm interested in when people die, I do what is called a time to event analysis, which is a curve like this. Everyone is present here. Every time someone dies, I go down one step. And this is time. So every one of these steps in the curve is a death. You start with everyone alive, and then you'll go down, and you see that after 60 months in this population, there is really almost no one surviving 5 years. Those receiving chemo, they are on the black line. Those receiving no chemo, they are on the dashed line. And you see that the black line is a few months ahead of the others. This means that this kind of chemo gives a constant gain of a few months of life. If you do the proper math and you compare all the points down the curve, you calculate an hazard ratio that is 0.77. The hazard ratio is a sort of an average measure of the distance of these two curves. And it tells you that on average, those on chemo survive 23% more time than the other. If you translate this in time, is a 9-week difference on this scale. So these two curves are 9 weeks apart. 9 weeks is less than 2 months, but is better than no week at all. Then you will need to discuss with the patient if he wants to take the cost and the side effect of this chemo, where the expectation for him is to, wherever he was supposed to die along this curve, taking chemo, on average, he will survive 9 weeks more. That's what the hazard ratio indicates. Okay, so relative risk, odd ratio, hazard ratio. Then we have one study, and then someone else does a second study, and then a third study, a fourth, and so on. And now we get to, okay, how can we find an average measure across studies? That's what meta-analysis does. First of all, you know what the difference is between a systematic review and a meta-analysis? Anyone? Please. The forest plot. Okay, so the forest plot is meta-analysis. And what is instead the systematic review? Okay, so but you are right. So the systematic review is searching the literature for all the studies answering a specific question. is a systematic search of all the studies about, I don't know, cisplatin effect in improving survival in breast cancer. A meta-analysis is a summary plot with a final number that tells you, across all the studies I found in my systematic review, the average effect of cisplatin on breast cancer mortality is a number. So, in a way, you cannot have a meta-analysis if you don't do first a systematic review. You could do a meta-analysis of 3 studies. For any reason, you don't search all of them. You have 3, and you use meta-analysis to pool the 3, to make the average. Sometimes pharma does so. They have 3-4 studies on one specific molecule, and they want to present a single result. And they do a meta-analysis without a systematic review first. But if you want to really try to understand what's the bottom line on some drug effect, you do first a systematic review, and then a meta-analysis. Now, a systematic review is based on a PICO question. You have to be precise on your population intervention comparator. You try to identify all relevant studies. We will have a specific unit on systematic review, and you will see how you assess if the search was done properly. These studies are appraised for their quality. So you don't take them all as they come, but you try to see if they are all of the same quality, and if not, you try to see if those better done give the same result as the other, or they point to more effect, less effect. And finally, they provide you a summary of the evidence, meta-analysis or not, in a standardized way. So, systematic review means that all the studies were included. The concept of including all the studies stems from the concept of p-value. P-value is the probability that repetition of an experiment gives the same result. Now, to be sure that you appraise the true underlying effect, you don't want to select only the positive study or only the negative study. You want to be sure that you capture them all. Because if it's true that those are only repetition of the same experiment over and over, they are all giving you snapshot of the underlying reality. You want to be sure you capture them all. Also, a well-done systematic review should be reproducible. They will need to tell you enough of what they did that if you have really nothing to do for the next month, you can go there and do it yourself. You read the paper, you do the same search, you apply the same criteria to include, exclude, you extract the same data, you redo the meta-analysis, you should see the same result. It's like a true trial. It's not, I read the paper, I'll give you my opinion. It's not my opinion. It's objectively assessing the evidence in a way that can be reproduced. There are 2 basic underlying assumptions that make a meta-analysis and a systematic review worth our attention. One is we have to assume that since all the studies answer the same question, the only true difference between the studies is the underlying population. Is a random sampling of population that is tested over and over with the same intervention. And the second is that the peer review publication process is efficient. You know, I do a study, I write a grant, got some dollars, do a study, and then I write up a report, I send it to a journal. And it can get published or not. What the journal does, they look at the report and they say, oh, it might be interesting. They send it out to peer reviewers, other researchers, that they criticize the paper, and they say this was well done and this other part was not, suggest changes, goes back to the editor, and you receive a letter saying, sorry, we can publish it, or we can publish it as is, almost never happen, or they say, we would publish, but you have to address this concern, you have to do these changes. Now, what makes the success of a journal is how many times their published studies are cited in other publications, what is called citation index. The journal, unless few journals that are supported by government or by scientific society, most journals, they live by selling space for advertising. So they sell pages to pharma, where pharma put advertising of medication. And of course, the more the journal is read by people, the more copies are read, and the more often the papers published on the journal are cited in other research, which is a proof that people read that journal, the higher the price to put advertising on. So when you think of New England Journal index, impact factor 50, or I don't know, Annals of Internal Medicine impact factor 17, British Medical Journal impact factor 12, that number is the prestige of the journal, but is also how much it costs to put advertising on. And it's very difficult to publish negative studies on big impact journal, because a negative study, almost no one will cite. A study saying, you know, laparoscopic approach to cholecystectomy and open abdomen approach, there's no difference. It's not really a sexy study. It's much better to say, you know, laparoscopic, we got 2 less days in the hospital, same rate of complication, and no infection. That's sexy. And the same is for medication, showing that aspirin, or I don't know, that the new antihypertensive is no better than the old one. Who cares? Why? Showing that it's better. For this reason, the peer review process and the editorial process in general tend to facilitate publication of positive result. This is a bias, because then the systematic review and the meta-analysis will only sum positive study. All the negative study that were not published, you won't see. And that's a problem. Now, the meta-analysis, as the colleague was suggesting, is a way of calculating an average effect, a common effect. What's the gain? The gain is that if you have 4 studies of 100 patients, you have started to make consideration about precision. You have 4 studies with 100 patients each, even if they are identical and their estimate fall at the same place, they will have a large confidence interval. If you pull them together, you sum up 400 patients, the estimate stays where it is. You don't learn anything about the estimate, but the confidence interval shrinks. So you gain in precision by doing meta-analysis. We have covered this concept already. This is systematic review. Meta-analysis is a subgroup of systematic reviews. And as I told you, there are some meta-analyses that do not have a systematic review backing them up. The way you present the result is the forest plot. So you have each line is a study. You have the treated group, the control group, how many patients, how many events for each group. And you have a summary effect size measure. In this case, it's an odd ratio, and is 0.68 for this study, 0.61, 0.90. In this case, is not significant. And then you have a summary estimator. The studies, they have a dot for the average effect size, and the confidence interval is a bar. The pool is a sort of a losange, where you have the thickness is how big the total population is, and the width from one tip to the other is the confidence interval. Again, if this doesn't cross the line, means that there is an effect going this direction, maybe favor the treatment. If it was on the other side of the identity line, would favor control. Now, when you put all the studies together, you may consider them all the same, or you may give a different weight to different studies. This is what makes the difference between the fixed effect and the random effect. There are different ways you can consider the study different. For example, the larger study, the more consideration. But also the more event, the more consideration. Because if you have a study with 10,000 participants, no events, it's difficult to tell if the treatment or the control was better. There were no events, so they were identical. If you have a smaller study, say only 2,000 patients instead of 10,000, but higher risk, and there were a lot of events, say 10% event rate, well, that study provides more information. So in the end, what you usually use as a weight is the precision. So a balance between the event rate and the sample size. We'll go back to that in a second. Before going back to what makes the difference between the weight you use for fixed random effect, I want to point to you one consideration, which is critical to understand why we need meta-analysis. If you just sum up all the patients, say you have a set of studies, you just sum up the patient, sum up the events of the treated and the untreated. And then you consider this as a single study where you say, okay, overall I treated 1,100 and I got 400 events. In the control, 925, 300 events. So there is a relative risk of 106. You consider this as a big single study, you get something. If you do the proper thing, so you compare each group, each control, within each study, each treated group with their control, you calculate each single risk ratio, and then you give the appropriate weight, you come up with something different. Here it goes in one direction, is in favor of control. Here is in favor of the active treatment. Not a lot of difference, is 06 and 04, but it goes in different direction. You cannot just sum up. If you sum up, you lose the gain of randomization, because randomization was within each study. So you have to compare within each study and then sum up. In summing up, which you have to do, if this is for sure wrong, this may be right or wrong, depending how you apply the weight. And the weight are different in fixed and random. I think we can skip this one. This is the concept that one study, this is really about the p-value. One study does not include the true difference. If you assume that the blue one is the true difference, all the studies have that true difference in their confidence interval, but out of 20 studies, one does not include the true difference. That's just by statistics. It's not that that study is wrong. That study is the one in 20 or the 5 in 100 that do not include the true difference. And the other concept here is that in this study, the variability for patient was from here to here of the effect. In this study was from here to here and so on. This losange here is where very likely the average of the study will be. And you see, it's much less spread apart. But you cannot use this here. So the effect here is, say, 2 times from 0.80 to 3 point something. But the effect is from here to there. If you try to apply these to studies, this is where the average value of the next study will fall, the average. But the distribution is really from the lowest study to the highest study. So if you try to apply this information to patient, what counts is this spread, the one that is covered by all the study. For your next patient, the effect can be here or can be here. For your next study, the average effect is the one that is represented by the losange. So, to recap, bias can arise from the study included in the review. If you include bad studies, or studies with poor quality, your estimate can be biased. Bias can arise from studies not included in the review. If negative studies are not published, that's what biasing your review. You will tend to show an effect when there is no effect there. Or you can be the one creating bias if you do your meta-analysis improperly. And here is where it comes to the fixed effect and random effect. In the fixed effect model, you just use as a weight the inverse of the variance. So that's really saying the larger the study, the more event, the more weight, period. And you assume that all studies come from the same population. All trials estimate one single underlying effect. Sometimes that's not true, and your meta-analysis show heterogeneity. It's a statistical test, usually is reported at I-square, and you are happy if I-square is less than 30%. If it's higher than 30%, you say, very likely this population or this intervention are not exactly the same. If you ignore heterogeneity, your confidence interval will be falsely narrow, and you can conclude that the intervention works when in reality it does not. Also, if there is a different performance of that intervention, if aspirin works in all studies with the exception of 3, you have to look into those 3 studies. Maybe the population is slightly different. Maybe aspirin was given in a different way. Maybe there were co-medication. And you learn a lot when you do systematic review and meta-analysis, and you find heterogeneity. If you explore heterogeneity, you usually learn something about the intervention. There are 2 things that have to stem from, this is the standard way. You assume initially all the studies are exploring the same phenomenon. You explore heterogeneity. If you find a reason for variability, if some studies are different, you take them out. If not, you use the random effect model. In the random effect model, you just assume that there is some variation that is beyond chance. The effect is that it expands the confidence interval. It tends to be more conservative. You do not risk to assume that an intervention works when in effect it does not, but you may lose, if you just do the random effect, you may lose intervention that they do indeed work in a subgroup of studies, or they do indeed work, they just show up as non-significant here. The last point on meta-analysis, you will read more and more network meta-analysis. Now, network meta-analysis are complicated from the statistical viewpoint, but they are extremely useful for clinical practice. And I'll spend a minute to explain you why. When you want to prove that a new antihypertensive works, you have to test it against placebo. And the reason is that if you test a drug against another drug, and the one that you use as control does not work, you can show that this one works, or this is no worse than the one you have available, when they both do nothing. Just because if you compare an antihypertensive with a non-effective antihypertensive, this is non-effective, this is equal to that one, and you assume, okay, it works like the other. So FDA will not approve a new medication unless it is tested against placebo to show that it works. Now, when it comes to you don't decide to prescribe a medication because it's better than placebo. Usually, unless few cases where there's only one treatment available, your question when you are with the patient is, do I prescribe A or B? So what you are interested in is this new medication that I'm happy you showed against placebo works, is better or worse than this other medication that I have that is maybe cheaper, is maybe well known for side effect and so on. Or vice versa, the new one is, say, equally effective but better for some other characteristics. We need comparative effectiveness study, and there are very, very little. So network meta-analysis try to save this time. If there is a comparison A to B, okay, we use A to B. But if A to B is not available, and that's the question we are interested in, network meta-analysis does what we do anyways in our mind. If we know that A is better than placebo and B is better than placebo, we try to guess who's better among the two. One way of doing that network meta-analysis is to find if these two are sufficiently enough that we can trust this indirect comparison, or if there is some direct comparison, network meta-analysis put together the direct, say there's one study comparing A to B, and then there are 20 studies comparing A with placebo and B with placebo. It builds a network, and it learns about this comparison from both the direct comparison and the two indirect comparison. So, for example, in the field of antipsychotics, there's a lot of evidence comparing fluoxetine against paroxetine, against venlafaxine, against sertraline. But if you build a proper network, you can get the comparison among all the different drugs, both learning from the direct comparison and all the other steps in the network. It's pretty complicated, but it helps you choosing among different drugs. Anyone still alive? Good. We have way of killing the last survivors. I have 3 more concepts for you. Common problem with RCTs. You have discussed baseline balance in risk. And of course, not to scare you since the beginning, we had built the example with balanced study, but there might be non-balanced studies. Protocol violation, lost at follow-up. We'll be quick. 3 concepts. I said quick. I didn't say painless. So 3 critical components. How we deal with prognostic imbalance. Sometimes we do randomization, but the study is still unbalanced. And what do we do if patients do not adhere to therapy? How we can try to save the study? And finally, how do we judge the loss at follow-up? I think you had discussed this in your groups. Let's try to recap how to go with these 3 aspects. So, adjustment, how to correct for baseline imbalance. Why we do randomize? To get 2 identical groups. The baseline levels, their prognostic factor, and the prognostic factor for the outcome of interest. If you are unlucky, you may have in the treatment group, say you are building 2 groups of 100 patients. In the treatment group, you end in having 80 young patients. In the control group, 80 old patients. I mean, this is really unlucky. But let's use the extreme example to show what happened. Now, the treated group does better, of course. It does better for the treatment, or it does better because you have many more young patients. If you believe that it's treatment, you have to be able to prove it, because I might say, no, it's just because you have younger patients and they do better no matter treatment. How can you prove when you have an imbalance like this that the treatment is responsible for the effect. Sorry? Stratification, right. And please, stratification is like considering the young and the old, two different studies. You calculate the effect in the young and the old, and then you pull across. It's like doing a meta-analysis of two different studies. So what you do is you compare treatment and control in the young and treatment and control in the old. This is stratification. You realize that your study is unbalanced for age, you create two strata for age, and you do the analysis by stratum. So let's assume that the treatment effect is 1. Let's assume that there is no effect of treatment. And the event rate in the old is 40%, in the young is 10%. This is I don't know, is deaths for some causes. Young, they die much less than old. Now, if you look at your population, and we assume that there is no effect, and the event rate is 40 in the old and 10 in the young. In the treatment group, you have 80 old, which means you will have 80 young, 10% you will have 8 events, 20 old, 40% you will have 8 events. In all, you have 16 events. In the control group, you'll have 2 events in the young, 10%, 32 events in the old, 40%, and you have 34 events. And if you consider just the event rate in the 2 groups, you get 0.47, 16 divided by 34. Now, if you consider that in the young there were 8 in 80, I take the same number here, but here I was summing up by treatment group. Now I'm summing up by age. So in the treatment group of young, I had 8 in 80, 10%. In control, I had 2 in 20, 10%. The relative risk is 1. In the old, 8 in 20 treated, 40%, 32 in 80 untreated, 40%. The relative risk is 1. If I do a meta-analysis, 1 and 1, I get 1. So if I do the proper analysis, the treatment has no effect. And you see here, in the young, no effect. In the old, no effect. But if I was to mix them up like here, I would see a 50% reduction, just because there was imbalance. Now, you can imagine that the situation is more complicated. I might have young and old, diabetic and non-diabetic. And in a control group, I can have the reverse, both for young and old and for diabetes. Of course, if you are so unlucky, you'd better choose another job. You stop randomizing patient and you leave someone else to do the randomization. But if you really want to continue, you have to stratify. Now you have 4 groups. So you do the analysis for each one of the strata. I'm not doing the numbers, don't worry, but you would do the numbers for young, non-diabetic, old, non-diabetic, young diabetic, old diabetic. You will calculate the effect in each one of the strata and then pull across. This is what a stratified or adjusted analysis does. The bottom line is, whenever there is an adjusted analysis and you recognize that they are adjusting for reasonable confounder or reasonable risk factor, trust the adjusted analysis. If they are adjusting by zodiacal sign, city of birth, or color of the hair, maybe they are just trying to making it up. Because of course you can adjust to see clearer or adjust to confound. But if the risk factor for the adjustment are reasonable, go for it. Intention to treat. Intention to treat is an attempt to save from the fact that some patients do not get treatment. Do we include them in the analysis or not? Yes. And what we assume for their outcome? Because they didn't receive treatment. We count them in the treated group or in the control group? as they were. So even if they didn't get treatment, we count them in the group where they should have been. And what if they were lost at follow-up? Also, but we don't know what happened, what we assume for them. They had the event or not? They had the event, okay. So it's not only important to include them, but to make assumption about where to include them and what happened. Now, again, let's consider an hypothetical study where there was no effect. You randomize 100 and 100, 20 have the outcome in the control group. In the treated group, only 80 took the treatment, 20 they did not. But we follow them, and those 20 who did not, we know that 12 had the outcome. Of these 80 that took the treatment, only 8 had the outcome. Now, if you do the analysis per protocol, you do not consider the non-adherent, you will have 8 in 80, 0.2, and you will have 20 in 100, 0.2. And the relative risk would be 0.5. If you include also the 12 events in the 20, so 20 in 100, you will get a relative risk of 0. So you see how important it is not to disregard this portion. If I don't count those not getting treatment, I may say that there is an effect. In reality, since my intention was to treat 100 patients, I don't really care. If this medication was difficult to take, was causing side effect, in the end, in this group, I got 20 events. In that group, I got 20 events. 8 in those taking the medication, good medication, but those who were unable to take it, they still got the event. So we have to count them in the group where they were. For the lost at follow-up, if you consider 1,000 patients per group, and you have 30 lost at follow-up, 3% per each group, and you have a 3% mortality, say in the control, or 3% in the active group and 6% in the control. So there is an improvement here. There's a 50% reduction in mortality. Now, if I calculate the relative risk, 3 over 6 is 0.5. There's a reduction. If I include also the one lost, and I say, well, these were all dead, these were all dead, the result is that I will have 30 plus 30 on this side, and I will still have 60 on this side, and because I assume that these were all dead and these not, and I might lose the effect. Of course, this depends. In this case, the lost follow-up rate is very close to the event rate, and I may have a different result. If instead the numbers were different, so the mortality was 20%, even if I pull back these lost at follow-up, assuming that these were all dead in the treatment group and these were all alive in the control group, I will go from 0.5, the same, adding the 3%, this will become from 200 to 30. This one will become from 400, will stay, 400, because I assume that this had anyways no bad event, and I will go from 50 to 57. There's still a difference, but it's much less. The lost at follow-up need to be accounted for. I have to count them as events in the control group, non-events in the, as events or in the treatment group, non-events in the control group, but even if I do this worst case scenario, what really counts is how different the event rate is from the follow-up rate. If they are close, the difference will be minimal. But if they are close, the difference can be high. If they are different, the difference can be minimal. Sorry, I made it almost continuously the opposite, but the concept is that I have to account for lost at follow-up. I have to be worried when the size of the lost at follow-up is close to the size of the event rate. So prefer ITT whenever possible. always consider the worst case scenario or reasonable assumption in between. Of course, if you have two studies, one is without lost at follow-up, the one without lost at follow-up is the one you would prefer, because all the other are assumptions. We assume they will be dead, we assume they will be alive, but we don't really know. So for how cautious we can be, we don't know the truth. I have 3 slides making up the take-home messages. I hope that you got the point that the relative and the absolute risk reduction are different. The relative measures of effect, relative risk, odds ratio, hazard ratio, are all similar. They help us understanding if there is an effect, but they don't tell us what is needed for decision making. They are good for pooling, they are good for meta-analysis, they are good to compare between different treatment, but when you want to assess the impact on a clinical decision on a population, you need absolute measure of effect. The absolute risk reduction, the risk difference, or the number needed to treat. Meta-analysis is a mathematical method to obtain an average effect across many RCTs, or the same concept can be applied within a study, within a randomized study, to save the effect of randomization. You can have meta-analysis of non-randomized studies. You can have meta-analysis with indirect comparison. The science is not as advanced as for standard meta-analysis. And finally, adjusted analysis, good to have, particularly when groups are imbalanced. ITT help you maintaining the balance at the beginning. Lost at follow-up may or may not impact depending on how many you lost as compared to your event rate. If someone survived, can go home by now. Thank you.